Electrons are supposed to be particles. That's not a theory. That's not a hypothesis. Every circuit in your phone, every wire in your walls, every quantum computer being built right now assumes that electrons behave like tiny, trackable things moving through materials with definite speed and energy. 3 weeks ago, a team in Vienna watched the electrons stop being electrons. They dissolved. They lost their identity. And then those identityless electrons did something that physics said was impossible. A paper published in Nature Physics contains a sentence that should not exist. Quote, topological properties can even arise because particle-like states are absent. End quote. Properties emerging because particles are absent. That's like saying you can have a river without water, a symphony without instruments, a footprint without a foot, except physicists just proved it's real, and the implications reach from quantum computers to black holes. For nearly a century, we've operated under a comfortable assumption. Electrons are particles. Sure, they're weird quantum particles with wave-like properties, but at the end of the day, you can point at an electron and say, there it is, moving from here to there, carrying this much energy at this speed. This assumption is so fundamental that it underpins everything from your smartphone to proposed quantum computers. It's called the Quasiparticle Picture, and it works so well that physicists basically forgot it was an assumption at all. Then a team in Vienna cooled a crystal to a fraction of a degree above absolute zero, and the electrons stopped being electrons. The material is called Cerium Ruthenium Tin, chemical formula CeRu4SN6. It's been sitting in labs for years, labeled as a failed insulator, because it refused to behave the way theory predicted. Standard physics said this compound should become an insulator at low temperatures, meaning electricity shouldn't flow through it. Instead, it kept conducting. Scientists shrugged and moved on. Failed experiments happen. But Diana Kirschbaum and her colleagues at TU Wien weren't satisfied with failure. They decided to look closer at what was actually happening inside this rebellious crystal. What they found is forcing physicists to rewrite the rules of quantum matter. To understand why this discovery matters, you need to understand what electrons are supposed to do. In most materials, electrons zip through the crystal lattice like tiny billiard balls. They bump into things, scatter off atoms, but they maintain their identity. You can track them. You can measure their speed and energy. Even in the strangest quantum materials, even in superconductors where electrons pair up and flow without resistance, you can still point at the charge carriers and describe what they're doing. This is actually surprising when you think about it. A typical piece of copper contains something like 10 to the 23rd power electrons, all crammed together, all repelling each other with electromagnetic force. It should be chaos. It should be a screaming mess of interactions where nothing makes sense. But in 1956, a Soviet physicist named Lev Landau figured out why it isn't. He showed that even when electrons interact strongly, the excitations in the system behave like independent particles. He called them quasiparticles. They're not real particles in the philosophical sense. They're collective excitations, patterns in the quantum field, but they act like particles. They have definite energy. They have definite momentum. And crucially, they have definite velocity. You can do math with them. This is the foundation of modern electronics. When engineers design a transistor, they're implicitly assuming Landau was right. When physicists discovered topological insulators, the exotic materials that won the 2016 Nobel Prize, they assumed Landau was right. The entire field of topological materials, materials with properties protected by mathematical knots in their electronic structure, requires electrons to behave as identifiable entities moving through well-defined energy bands. Think of it like this. Topology is about shapes that can't be smoothly deformed into each other. A donut has a hole, a sphere doesn't. No amount of stretching or squishing can turn a donut into a sphere without tearing it. This is why topological materials are so exciting for technology. Their special properties, like surface currents that refuse to scatter, are protected the same way a donut's hole is protected. You can dent the donut, scratch it, even take bites out of it. The hole survives. Similarly, topological electronic states survive defects and imperfections that would destroy ordinary quantum effects. But here's the catch. To define these topological shapes, you need something to shape. You need the electron energy bands. You need the quasi-particles tracing out paths through momentum space. No particles, no paths. No paths, no topology. This isn't just a practical problem. It's supposed to be mathematically impossible. Cerium Ruthenium Tin doesn't care about supposed to be. This material belongs to a class called heavy fermion systems. The electrons in these compounds interact so strongly with localized magnetic moments, specifically the F electrons in cerium atoms, that they behave as if they have hundreds of times their actual mass. They're sluggish, heavy, on the verge of stopping entirely. And cerium ruthenium tin sits right at the edge of a cliff called a quantum critical point. A quantum critical point is where a material can't decide what it wants to be. Imagine a coin spinning on a table, never landing on heads or tails, just spinning forever. That's what happens at a quantum critical point, except instead of heads or tails, the material is fluctuating between two different quantum states. At normal temperatures, thermal energy kicks the system one way or the other, but at absolute zero, there's no thermal energy to break the tie. The material just fluctuates forever, quantum mechanically. And in this fluctuating state, the quasi-particles die. Their lifetime becomes essentially zero. The constant scattering from quantum fluctuations means an electron can't maintain its identity long enough to be tracked. It doesn't have a well-defined energy or momentum or velocity anymore. As Kirschbaum put it, the quasi-particle picture loses its meaning. The electrons, in a very real sense, dissolve into a puddle of quantum waves. They stop being particles. According to everything physicists thought they knew, this should destroy any topological properties. The mathematical donut should collapse into meaningless noise. You can't have a knot in fog, except they found a knot in the fog. The smoking gun was something called a spontaneous Hall effect. In a normal Hall effect, you apply a magnetic field to a conductor and the electrons curve to one side, creating a voltage perpendicular to the current. It's basic physics, discovered in 1879. But in cerium ruthenium tin, below 1 Kelvin, with no magnetic field applied at all, the current bent sideways anyway. Let me be clear about how strange this is. The electrons, which no longer behave like electrons, which have no well-defined velocity or trajectory, somehow collectively decided to turn right. Something that isn't a particle exhibited behavior that only particles should exhibit. It's like asking a cloud to march in formation. And here's what really broke the theorists' brains. The effect was strongest exactly where the quantum fluctuations were most intense. Right at the quantum critical point, where electrons are least particle-like, the topological signal peaked. When the researchers applied pressure or magnetic fields to push the system away from criticality, to calm down the fluctuations and restore normal electron behavior, the topological effect vanished. The quantum chaos wasn't destroying the topology, it was creating it. The team mapped out the phase diagram, essentially a map showing which state the material is in under different conditions. The topological phase appears as a dome shape centered exactly on the quantum critical point. Move away in any direction, toward more ordered states, and the topology disappears. The name they gave this new state of matter is an emergent topological semimetal. Emergent because it materializes from the collective behavior of the fluctuating system, not from the individual electrons. Chi-Miao Si at Rice University, one of the theoretical physicists on the team, developed a mathematical framework to explain how this is possible. The key insight is that topology doesn't actually require particles. It requires certain mathematical structures to exist in the equations describing the system. Specifically, it requires features called Weyl nodes in something called the Green's function, which describes how electrons propagate even when they're not acting like particles. Think of it this way. Imagine a vibrating metal plate covered in sand, like those Chladni plate demonstrations, where the sand forms beautiful geometric patterns. Normally, we see the patterns because the sand grains settle at the nodes, the still points. The grains are like quasi-particles, and the patterns they trace are like topology. Now imagine striking the plate so hard that the sand flies into the air, a chaotic cloud with no structure. The sand is gone, but the plate is still vibrating. The nodes still exist. The mathematics of the vibration haven't changed just because you can't see them with sand anymore. In cerium ruthenium tin, the electrons are the sand, And the quantum critical fluctuations are the hammer strike. The sand is chaos, but the plate is still ringing with topological structure. The spontaneous Hall effect is the sound of that ring. Now, I need to be honest about the limitations here. This is one material. The effect only appears below 1 Kelvin, which is colder than outer space. The topological signal, while genuinely large compared to conventional Weyl semimetals, is still subtle enough that measuring it required extremely precise experiments. And tiny magnetic fields, we're talking tens of millitesla, were enough to suppress it entirely. Some skeptics have raised the possibility that the Hall effect comes from disorder in the sample, from defects or strain rather than intrinsic topology. The team's response is that disorder effects would be roughly constant across different conditions. They wouldn't form a dome centered on the quantum critical point. The fact that the signal peaks at criticality and vanishes away from it strongly suggests this is the real deal. Others have questioned whether the quasi-particles are truly absent or just extremely short-lived. It's a fair point. Experimentally, it's hard to prove something is exactly zero versus just very small. But the team argues that the distinction is operationally meaningless. If the electron's lifetime is shorter than the time it takes to cross a single atom, calling it a particle is like calling a soap bubble a building material. Technically, it exists. Practically, it's gone. The theoretical framework is also new and not yet universally accepted. The idea of computing topological invariance from Green's function zeros rather than band structures is sound mathematically, but this is the first experimental evidence that it corresponds to real physics. Other interpretations will inevitably be proposed. That's how science works. But here's why the physics community is taking this seriously. The discovery doesn't just add another exotic material to the catalog. It bridges 3 separate fields that researchers had been treating as mostly independent. Strange metal physics, where electrons scatter at the maximum rate allowed by quantum mechanics. Heavy fermion systems, where electron masses balloon by factors of hundreds. And topological matter, where mathematical invariants protect quantum properties. This paper shows they're all connected. And there's a cosmic angle to this that I find genuinely mind-bending. At the quantum critical point, electrons scatter as fast as the laws of physics allow. There's a fundamental time scale called the Planckian time, roughly Planck's constant divided by the temperature times Boltzmann's constant. It's the shortest time that makes sense in thermal physics. The electrons in Cerium Ruthenium Tin scatter on this timescale. The same timescale governs the behavior of black hole event horizons. There's a theoretical framework called the ADS-CFT correspondence that relates strongly interacting quantum systems to gravity in higher dimensions. Under this correspondence, the strange metal behavior of materials like Cerium Ruthenium Tin is mathematically equivalent to properties of certain black hole solutions. By studying this tiny crystal at millikelvin temperatures, physicists are probing the same quantum dissipation physics that governs the most extreme objects in the universe. Whether this connection is deep or just a mathematical coincidence is still debated, but the fact that it exists at all is remarkable. What does this mean for technology? The researchers are careful not to overpromise. This is fundamental science, not an engineering breakthrough. But the implications are tantalizing. Topological materials are attractive for quantum computing because their protected states resist noise. Quantum critical materials are attractive for sensing because their extreme fluctuations make them hypersensitive to perturbations. Having both in the same system, as Chimiao points out, could yield devices that are simultaneously robust and ultra-responsive. That's usually an impossible combination. More practically, this discovery gives researchers a new search strategy. Quantum critical behavior is found in many material families. It has characteristic fingerprints in how electrical resistance and specific heat vary with temperature. Now physicists know to look for topology precisely where they would have previously assumed topology couldn't exist. At the edge of instability, in the quantum chaos, how many other emergent topological materials are waiting to be found? Nobody knows, but they now know where to look. There's something philosophically profound buried in this discovery. For a century, physics has successfully described the quantum world in terms of particles. Not classical particles, not simple billiard balls, but still identifiable entities with measurable properties. This works so well that we forgot it was a choice, a useful fiction that happened to match reality. Cerium Ruthenium Tin is reality politely informing us that the fiction has limits. The electrons don't stop existing when they dissolve into quantum fluctuations. They stop being particles. But the universe doesn't care about our categories. Properties we thought required particles emerge anyway, through mechanisms we're only beginning to understand. The researchers at TU Vienna initially hesitated to even test the theoretical predictions. The idea of topology without quasiparticles seemed so contradictory that they almost didn't bother looking. Curiosity prevailed, as it often does in science, and now we have proof that the universe contains states of matter that our textbooks said couldn't exist. As Silke Bühler-Peschen, who led the experimental team, summarized it, a particle picture is not required to generate topological properties. The concept can be generalized. The topological distinctions emerge in a more abstract mathematical way. Our experiments suggest that topological properties can even arise because particle-like states are absent, because they're absent. Not in spite of, because. Sometimes the deepest discoveries aren't new particles or new forces. They're realizing that something you assumed was fundamental was actually just a special case, that the rules are bigger than you thought, that nature doesn't need your categories to operate, a crystal that refuses to let its electrons be electrons, and in that refusal creates order from chaos. If you want more discoveries that rewrite what we think we know, I'll be right here, finding them.